Okay, I see it. We are online.
Perfect. Thank you, Simone. Sorry for this. Okay. Good morning, everybody. Good afternoon to our invited speaker. Welcome to this third and final day of the special courses at the National Observatory. I am pleased to introduce the speaker of this morning lecture, Professor Dr. Heike Rauer. Dr. Rauer got her undergraduate degree in 1986 by the University of Hanover, her PhD in 1991 by the University of Göttingen, and her habilitation in astrophysics, which I think is something equivalent to our Libre Docência in Brazil, by the Technical University of Berlin in 2004. After being a postdoctoral fellow at the former Max Planck Institute for Aeronomy, the Observatory of Paris-Meudon, and the Institute of Planetary Research of the German Aerospace Center, she became the head of the Department of Extrasolar Planets and Atmospheres of this later institute in 2005, and she is currently the director of the institute since 2017. She was also professor of planetary physics at the Technical University of Berlin and current professor of planetary geophysics at the Free University of Berlin. Her current research interests are focused on exoplanets, especially the study of their atmospheres and the search for biosignatures. She has been involved in the CORO mission as co-investigator and representative in the Scientific Council. Since 2011, she is also the co-principal investigator of the NGTS, the Next Generation Transit Survey, and she is now the principal investigator of the PLATO 2.0 Instrument Consortium, of which Brazil is one of the members. Dr. Rauer, thank you very much for having accepted our invitation, and it is a pleasure to have you here today with us. You may start when you were ready.
Thank you very much. Thank you very much for this kind invitation and a very nice introduction. So I'm very happy to be with you here and present to you PLATO. And I was assuming I don't speak to experts of exoplanets, so I have divided my talk into half. The first half, I will give you an introduction about extrasolar planets, what we know about extrasolar planets, also to motivate what we want to do with the PLATO mission. And in the second half, I will describe the PLATO mission, the PLATO satellite in a bit more detail. So let's start from the basics, and the basics are our solar system. I think you all know our solar system, but I want to recall it because it's our reference system. It's the system we know most, the most long, of course. It's the longest under astronomical investigation, but it's also the only system where we have life here on the third longest planet. If you look at the solar system, the distance here are distances in this illustration are not to scale, but the sizes are to scale. And you notice immediately there is a very striking what we call architecture, that is the dependence on masses with orbital distance. So we have 4 small rocky terrestrial inner planets, followed by 2 gas giants made mainly out of hydrogen, helium, and then 2 smaller gas planets, so-called ice planets, still with large amounts of hydrogen, but also heavier elements in them. And this is a typical architecture. And at the beginning, of course, humans, we thought all systems would be like that. But as you will see, this is not the case. To give you some numbers, just to have in your mind, Jupiter is 300 times as heavy as Earth, 11 times the size of Earth, and has 11-year orbital period. And our outermost planet, Neptune, has 17 Earth masses, and it orbits at 30 astronomical units, with 164 years. So this is the size of our solar system. And the big question, and here we have a closer up look to the planets of our solar system. And as you can see, we know these planets relatively well, even for Moon and Mars. Here we see the NASA Perseverance rover on the Mars surface. We can fly there, we can land on them, at least in our neighborhood. We can send satellites to these planets and their moons and look at them in their detail. So we have a good idea what they are like. But of course, we cannot do this for extrasolar planets, which are tens to hundreds of light years away, and we are not able to get such a detailed picture of these planets. So the questions we have in extrasolar science is, are there other planets out there around other stars? And in particular, is there another Earth somewhere in our Milky Way or in the universe? And if so, is there life? And in a more general question, how do planets form and evolve in general? To understand this better also helps us to understand the evolution of our Earth better, because we can put the Earth into a larger context. So when you search for planets, of course, what we would like to have, because humans are somehow visual beings, we would like to see the planet, and we would like to have a photo of the planet, if possible, like in the solar system. But if that's not possible, at least as a dot in the sky. And here we see the latest on this with this technique from the James Webb Telescope. It was one of the first slides. First light results from James Webb. We have here a planet that has the mass of 10 Jupiters and orbits at 110 astronomical units from the star, so 110 times further away than the sun, than the Earth is from the sun. And you see images in different colors. So since the star, however, the star is so bright, a star is typically 1 million times brighter than the planet, it is not possible to just take a picture. You have to do something to be able to see the faint planet next to the star. So what is done here is a mask is put on the star, and to see where the mask is, they have added this white star afterwards into the picture to indicate the position of the star behind the mask. We don't see the star behind the mask. But what we do see is this bulb here, this point source, and this point source is the planet. So the distance from here to the center of the mask is 110 astronomical units. If you remember, Neptune orbits at 40 astronomical units from the sun. That means you could put the whole solar system behind the mask and you wouldn't see it. You wouldn't see it because it would be behind the mask. The only reason why here it is possible to take a direct picture is the fact that this image is taken in the infrared and the star is very young. It's 14 million years old, which means in terms of stellar evolution, it's a baby. Yeah? It's just born, and young stars are very hot, and it emits mainly in the infrared, or more light in the infrared than the sun does. So we can take this picture here, but it would not, with current techniques, it's not possible to take the same picture of the solar system, for example, and to take an image of an Earth or something. So that is the problem right now. We can take direct images, but only of very young and far away planets. And that what we would like to investigate is planetary systems which are analog to our own, so we can compare our own planets to these ones. And here we have to rely, therefore, unfortunately, for the moment, on indirect techniques. And the first technique that was successful to detect planets around other stars was the so-called radial velocity method. So this is a rather busy slide, but what it shows, it gives us here a little movie how this technique works. So we detect the planets indirectly, and what we are using is the fact that the planet and the star are rotating around a common center of mass, which is indicated here by this little blue dot. So the planet and star rotate around each other, and that means also the star moves with the same period as the planet revolves around it. And since the star emits light, and we can detect this light with a telescope, we can use the Doppler effect to measure the velocity of the star, the component of the star towards us or away from us. And this is what you see here in this in the bottom. We see a radial velocity plot showing the velocity of the star as it moves to us and away from us here in a nice sine wave. And the period gives us immediately the orbital period of the planet. And from the amplitude, we can estimate the mass of the planet. And when this data were taken, here you see an image. This is not a push 8 meter, 10 meter big telescope. This is a 1.9 meter telescope in the southern south of France. And this was work done for many years by Michel Mayor and Didier Queloz. They were finally successful in 1995 with this 51 Pegasi B planet, half a Jupiter mass, but an orbital period of only 0.04 AU. That is an orbital period of 4 days. So it is extremely close to the star and orbits the star in 4 days. This was debated heavily at the time, but then turned out to be true. And in 2019, Michel and Didier got the Nobel Prize for this discovery. So what we can, for our purpose here, what we should remember is that with the radio velocity method, we are able to determine the masses of the planets. To show why this was such a surprise, I want to show you this little movie. This movie is taken from the SOHO satellite, the Solar Heliospheric Observatory. And this satellite monitors the sun. It also has a coronagraphic mask, so a mask that, to block the sun. This is the red mask that you can see here. And it has the same effect as the moon in the solar eclipse. So it masks the sun, and what we can see is the corona, the atmosphere of the sun. For this movie, they have inserted in the middle images from another instrument on the same satellite that shows us how the sun rotates. But for our purpose, we should look on the corona. And I have taken an image of Jupiter and placed it at approximately the same distance that 51 Peg B has to its own star. So this would be the distance of 51 Peg to its star. And you can see what this means. This such a hot planet, such a planet so close to its star, is basically orbiting the star in its corona, in its atmosphere. And these stars are active, and you see these coronal mass ejections of hot energetic particles going to the planet. And you can imagine immediately that planets which are so close to the star, even if they are rocky and not gas planets, they would certainly not be habitable. You cannot imagine life there. And even for a gas planet, it's a very harsh environment. So that was heavily debated. It was really a big surprise that planets so close to the star could exist and work out. Meanwhile, there is a second method to search, indirect method to search for planets, very successful with the most discoveries to date, the so-called transit method. And the transit means that a planet passes in front of its star. So we are looking at the star. Of course, in reality, we don't resolve the star as it's done here, but for illustration. So we look at the star and we see the planet orbiting its star. And when it goes through the line of sight, you can see the planet will block some of the light from the star. So what we measure is the brightness of the star. We have a constant brightness, but when the planet comes, now let it come again, planet comes in front of the star, then the light drops, and when the planet is going, it goes back again. And the dip of this signal is proportional to the size of the planet. And in this movie, you see two examples. You see a big planet and a smaller planet, and they cause a different depth of the signal. So the transit method can do two things. First, this event, of course, happens periodically with every revolution of the planet around the star. So we get the orbital period, and with Kepler's law, the distance to the star. But from this signal, from this depth, we can have a direct measurement of the planet radius. So here we can determine the size of the planet. Of course, this method has a big drawback. It means we can only detect planetary systems where we see the planetary system edge on. So we see the side of the planet. We have to have the planet passing through the line of sight. And one can calculate the probability that this happens. And in fact, for these hot Jupiters, for the hot planets which are so close to the stars, the probability is around 10%. 10% of the time if you have arbitrary orientations of planetary systems, in 10% of all cases, we have a chance to detect it. For an Earth, the probability is only 0.5%. And for Jupiter, because it's further away from the star, it would be even more. The duration of this event, the duration of transit, depends on the orbital distance of the planet. So a hot Jupiter transits in typically 3 to 4 hours. But for an Earth, the duration of the event is 13 hours. And if you then think 13 hours, which happen only once per year, for an Earth around us. So these are about the numbers. Jupiter causes a death. This would be a drop of about 1% of the brightness of a star. For an Earth, it's 100 times smaller. So we are looking at something that's actually quite unlikely to observe, but if you observe many planets, many stars, then your chances, you have a significant chance to detect. And if you look at the exoplanet missions that already were executed or are running for exoplanets, there are quite a lot. We have, of course, the observatory type space telescopes like Hubble, Spitzer, or the James Webb. But dedicated missions for exoplanets started with the Kourou mission, a small satellite mission, which with German and Brazilian participation. And I think we were all happy to be part of this very first endeavor, followed by Kepler, test cubes, and we show examples, and then PLATO as ESA's M3 mission. M3 means M's for the middle-sized missions, and it's the third one in the Cosmic Vision program. We are planned to launch in 2026, and we will go into an orbit around the second Lagrangian point. That means we go in an orbit around the Sun with the Earth, so the telescope is always behind the Earth, and you look from the Sun, it goes around the Sun. It's the same orbit, by the way, as the James Webb telescope has. To introduce transits, I'd still like to show the Kourou light curves, not only because Brazilian was part of it as well, but because it's very illustrative to show. Here, what we see on the top is a light curve taken by the Kourou satellite. And you see this light curve is not like in the illustration. It's not a constant light curve over time. It's over time. But you see there is a periodic pattern here. This is because the star is active, the star has spot, it rotates, and therefore its basic intensity is far from constant. You see the rotation of the star. But what we also see are these regular dropouts here to the bottom. And here we see an enlargement of part of the light curves with these three events. And here you can see, for those of you who are not in exoplanet research, I can tell you, you have detected your first exoplanet here when you look at this light curve. This planet you would have seen looking at it with your naked eye. And when you search for Kepler citizen science, you will see that you will be able to scan through Kepler light curves, and there's a community who does that, also for tests, and you can see the large planets with your naked eye. Here we are talking about a planet of 1.5 Jupiter radii, 3 Jupiter masses, and it belongs to this new class of hot Jupiters, in this case less than 2 days orbital period. But what about if the planet gets smaller? And here we have also a type case for this event, for this type of planets, Kourou 7b, the 7th planet discovered by the Kourou mission. And what you see again is the light curve of the star. You also see it's far from constant, it varies over time, but you can't see regular dips here. And if you zoom it out and make a fit to the baseline, so it's flat, still, if you look at the data points, you don't see the transit. And here I've overplotted the transit that it was detected in the light curve, and you see it's well hidden in the noise. So you really have to accumulate a lot of data. And finally, if you co-add all these transits, this is what you have. So you have a picture textbook-like transit light curve of Kourou 7b, and here the dip is 0.03%. And this corresponds to a planet which is as small as just 2 Earth radii. And radial velocity follow-up observations, which are shown here, showed it's 7 Earth masses. This planet was the first rocky planet detected outside the solar system. So this was a milestone in the exoplanet discovery. Soon after NASA's Kepler mission, detected a very similar type of planet, and we will see there are now many of these hot rocky planets detected today. They are the most easiest to detect because they are so close to the star. But when you look at these planets, they are facing the same side to the star all the time, and the surface temperature on the day side is more than 1,000 degrees. So they are very, very interesting. It was a new class of planets, but if you think about putting the Earth into context, it's not what we look for. It's certainly not a planet that is habitable, so we can have life. But it was a big milestone. And then the Kepler mission was launched and operated until 2018. And Kepler gave us statistics. So what do we know about planets today? This plot is this type of plot is a plot you see very often in exoplanet science. And it needs a little bit of your imagination to understand this or to see what is really exciting behind this plot. So what does the plot show? The plot shows on the y-axis the mass of the planet in Jupiter masses. So here's one Jupiter mass. And on the x-axis, we see the distance of the planets to the star. So here we have one Jupiter mass, and here's Jupiter. Saturn, one is Neptune. And here below we have the terrestrial planets in the solar system, Venus and Earth. Here's Mars, and here's Mercury. And all the dots are known extrasolar planets. The colors indicate the different detection techniques, but we ignore these colors for the moment. We just take the dots as they are. And what you can see is that in this Mars distance diagram, there are areas which are filled with dots. There are areas which are completely empty. And then you have a substructure here. So what do we see? The first thing is that the dots are all in the upper left part of the diagram. Why is this? Because this is the part of the diagram that is accessible to current detection techniques. We can detect very distant planets only by direct imaging, as I've shown you in the first slide, but these are all very young systems. So we are not really able to detect an Uranus-Neptune-like planet today. More importantly, this parameter space here of the small planets, the terrestrial planets, is empty. We cannot detect Earth, Venus, pure Earth, Venus analogs today. We'll come back to this again and again. So here we have, to the lower right, we have white area, and of course, for PLATO, this is one thing where we want to go, fill this white territory. But then, if you look in this left part of the diagram, where we have access to with our detection techniques, even there, it is not homogeneously filled. So this is surprising, and this is new. We see a lot of planets which are here near Jupiter. So these are really Jupiter-like planets, gaseous planets, giant planets at moderate distances to their star. Then we have here a second block of points, and they are also around Jupiter mass, but very close to the star. They are these 51 peg-like things. 51 peg is somewhere here in the middle of this crowd. And in between, we seem to have a kind of desert of planets. And we see again a third block here. These are masses, planets which are so-called either super Earths or mini Neptunes, because they are in the mass between Earth and Neptune. And between these mini Neptunes and the Jupiter-like planets, there is here an area with less planets found. So we see substructure in this population, and this groupings has to be explained by planet formation and planet evolution theories. This was not expected, and of course, theory is now asked to help explaining this. Theory is also asked to explain why here we have some very close planets detected, and in between there's an area with no planets found. This is not a detection bias. If planets would be there, we would find them. It must have a reason. For example, that the atmosphere of a gas planet has evaporated here or whatever. There are several theories around to explain this. And of course, the big question is, how does this extend if we come to the small terrestrial planets or to the distant planets? We don't know. And I would expect that also there we will find substructures that give us constraints to planet formation theories. All right, so here I just said this new class of planets that are not found in our, not realized in our solar system, like the hot Jupiters, the super Earth, and the Neptune. All right, meanwhile, we have new and operating space missions in the sky. There is the TESS mission by NASA. NASA's mission has 4 small cameras, and they always observe 1/4 of the sky and then scan around the whole hemisphere. They have done so already twice, and just got mission extension again. So far, TESS has discovered 70 new exoplanets and more than 2,000 planet candidates that add to our list. And the good thing is they are all around bright stars, so we can get the radio and the masses. Why is that important? Well, I want to show an example. Here is a detection made by one of our postdocs here, Christine Lam. She was searching in TESS data, and she found a transit candidate. And this is the planet she found. It's only 70% of Earth's radius. It's half of Earth's mass. So it's one of the smallest confirmed exoplanets found at all. And it's interesting because it has a very high density of 8 grams per cubic centimeter. I don't know if you're familiar with this, but iron has a density of around 6 grams per cubic centimeter. Or silicates, and iron is high. So we are here at a planet that seems to be made mainly out of iron. And to study this, what the exoplanet scientists do, we place these detections in a diagram of planetary radii, Earth radii versus planetary masses. And the lines here, indicate planets with special composition. So a pure iron planet would lie on this black dashed line, and you see GJ367b is almost on the dashed line, so it's like it would be purely out of iron. Orange is the 80% iron. A planet like Earth would be close to this magnesium silicate line here, and you see Earth and Venus here. You see other small planets that are known and detected around other planets. They're all hot terrestrial planets. And so you can see if we have the radius and the mass of the planet, we can place it in such a diagram. We can compare it to a mass-radius relationships with different compositions, different assumed composition, and we can get a very first indication whether the planet is likely to be rocky, or where it is, if it's more made out of silicate or iron. Of course, it becomes more tricky if the planets are more heavy. Up here we have planets, you see here, which have a very large amount of gas, and then we enter an area of degeneracies because we have a core, we have a mantle, and we have a gaseous envelope, and it's more difficult to disentangle the different types of planets. But for these very small planets, it's pretty likely they are rocky, and here we can start to address differences between these planets and see what is a typical planet, for example, around a typical type of star. And this is just to show in the solar system. In the solar system, if you look at density versus radius, you see, for example, Mercury sticks out. Mercury is much smaller than the Earth, but has the same density. And this is because Mercury has a huge core and only very shallow mantle. And maybe GJ367 is the same. So that raises the question whether there are more Mercury-like planets around in other planetary systems. So here we have another example. I don't want to go into detail with the Cheops mission. Cheops is ESA's mission currently in orbit for extrasolar planets. Cheops is not searching for new planets. Cheops is built mainly to take very high precision transit light curves to get very precise radii of planets. And it's, for example, following up many test candidates to refine the radius, but in some cases it even detects more planets that TESS missed because TESS already moved to the next field. That has happened as well. So the main conclusion from this is that if you have masses and radii, and you start to think about what type of planets is it a gaseous giant? Is it this mini Neptune-like thing where we don't know how large is the core? Is there water? Is there ice? Is there an atmosphere? And up to terrestrial planets where we are talking about the size of the core in relationship to the mantle. It's all very exciting, and the exoplanets are apparently much more diverse than we previously thought. And but one thing is for sure, none of the systems that we have found so far is really like our solar system. We see new types of planets, we see different configurations, we have not understood it all, but we are still searching for a solar system. And what we are in particular searching for is planets in the habitable zone. I've used the word habitable already a few times. What does it mean? Habitable for us astronomers, habitable in general means a planet has the ability to develop life. It doesn't mean it has life, but it has the potential to have life. And the potential is what? For us astronomers, it simply means it has liquid surface water. So this is a simplified view, but it's a view that we can tackle, that we can address. Because if we take, let's assume an experiment, we take the Earth and we move it outside, we move it further away from the sun. At some point, the whole water or oceans would be frozen, the whole Earth would be frozen. And at that point, we don't have water anymore on the surface, so it would be too cold to develop. If we take the Earth and we move it to the sun, it will get hotter and hotter and hotter, and at some point, all the oceans and all the water has evaporated and lost to space. And then we are arriving at a planet that's too hot to have liquid water to be habitable. So you see, there is a distance around this star where the energy the planet receives from the star is just right, so water can be liquid on the surface, and we call this planet habitable. And this is what we are looking for. Do we have such systems? Do we have planets in the habitable zone of other stars? Yes, we have. We have the TRAPPIST system, the most famous in the moment. It's a system with 7 small planets, 7 terrestrial planets, and two or three of them orbit in the habitable zone of TRAPPIST. So this is really exciting, and a lot of numerical studies go on about this system now. But in terms of further search, can we tick this off? Can we say, yeah, job done? We found an analog system, and unfortunately we cannot, because the central star of the TRAPPIST system is not a solar-like star, it's an M-dwarf star. Here's a comparison between a solar-like star, M-dwarf star, and Jupiter, just to get a size difference. And M-dwarf stars are much cooler than the sun. They emit in the red spectral range, but many of them are also much more active in terms of energetic particles. So I recall the Soho movie. Something like that would also happen to a planet in the habitable zone around an M-dwarf star. So it's not clear how similar to the solar system planets these planets orbiting M-dwarf stars really are. Yeah, this is a field on its own.
Hi, sorry, your sound is missing.
What is missing?
Your voice.
My
No, now it returned. By it was for a little while you are explaining this slide.
Yeah.
Your voice was missing.
I'm sorry, I don't know how much you missed. I have not changed anything here. I just go on, I repeat a bit. And
yep.
Yeah.
Okay.
Okay. So the main message from this slide is we have TRAPPIST-1, very exciting, with rocket planets in the habitable zone. And this gives rise to many numerical studies how habitable these planets are and what could be detected. But planets orbiting M-dwarf stars have very different conditions to the two planets orbiting solar-like stars. So we still have to search for solar analogs. And what do we know about small planets around solar-like stars? Well, the best statistics we have is still from Kepler, from this Kepler mission, Kepler and K2. The Kepler mission data have been reanalyzed, and there are 2 publications in 2020 that came out, homogeneous independent analysis, and here's the result of one of them. So we know from Kepler that every star in the sky has a planet. And we know that 17% of these stars maybe have a super Earth. Yeah? But what they have shown here's the radius versus the orbital period, and the color and numbers in these boxes in this pattern gives you the probability for a small planet. And what you see is that the lower right, where we have orbital periods of the Earth, and one is the distance of the Earth to the Sun. You see here it's all gray. And even in the boxes here, the error bar is larger than the data value. So here we have no result from Kepler. We have, Kepler was not able to constrain really the frequency of small planets in the habitable zone of solar light stars. So this is a very important but yet open issue, and it's clearly the main search range for Plato. Why do we want to do that? Well, if you look at the evolution of the Earth, and this is an illustration on the points, you think about the Earth. When the Earth was formed, it was a hot magma ocean planet. Yeah, it was hot, and everything was molten, and then it cooled, and the crust was built. Plate tectonics came, and we had a secondary atmosphere outgassing from the interior. So the atmosphere of the Earth was it was in CO2 atmosphere, and life developed on the Earth in the CO2 atmosphere. In the oceans until life produced so much oxygen in the ocean that it bubbled out. And today we have an atmosphere of the Earth which has 20% oxygen, and most of the CO2 and the carbon is buried in the carbon calcium layers on the ground, on the surface. So you see, it's a very peculiar evolution of the planet. And you may think, well, what would have happened if there would have been less initial water or less water coming from comets and asteroids to the planet? What would have happened if we would have more water or more continents? And you can think about terrestrial planets where the prime parameters are very similar to Earth, but yet the conditions on the surface are very different. And to address this and understand how planets evolve, terrestrial planets evolve, I think we need more comparison objects, not only Mars and Venus in our solar system, but also around other solar systems. And please don't forget, when we look at the stars in the sky, they are not the same age. We are seeing stars which are just born, like the James Webb case, the baby star and the baby planet, therefore. And we will also look at stars that are older than the Earth. So here I have the big dream, and this dream is going beyond Plato, also including what we learn with future missions. We will be able to really compare our system and our Earth to other Earth-like planets at different stages of evolution. And this is the big picture where Plato wants to take its puzzle piece and make a significant contribution. So this is just summarizing it again from a different perspective. We have the stellar mass versus orbital distance of the planet. We have here Mercury, Venus, and Earth. And the green band is the habitable zone. And for small planets, the M-dwarf planets are down here, low mass stars. The habitable zone moves closer and closer to the star. Here's the TRAPPIST system. Yeah, this is what we know. But the habitable zone with small planets, rocky planets, extrasolar planets, you see it's empty. We only have the solar system planets, and we want to fill this with planets here from Plato. If you look at the numbers, I looked the numbers up a couple of weeks ago, 5,202 planets known, published on this webpage. You can check yourself now. From these, we have about 1,200 where we have a mass and a radius, so we can determine the density. And only 170, which we would call super Earths, so really the small planets, and none of them is in the habitable zone of solar-like stars, and none of them is here. And this will remain so until Plato. And that's the one big goal of Plato. And the other big goal of Plato is to really characterize these planets. That is, not only detect them, but get the radius, get the mass, and put them on this radius mass diagram. Yeah, with a small error bar, with a small error box in radius and mass. Why? Because when you look at all these lines of different compositions, to really place your planet, you need a small error bar, not to cause too many possibilities. So what Plato wants to do is get the radius with 5% and 10% in mass for an Earth-sized planet around the solar system. Now, it's not only about planets, and this is just a bit because I know the stellar community is very strong in Brazil. And the point here to make is simply that to get the parameters of the planets, we also need to determine the parameters of the star, and in particular the age. And PLATO is here building on Corot. Corot has performed astroseismology, so determined the eigenfrequencies, the pulsations of the star from the photometric light curve. And this was very successful. It was also done on Kepler light curves. And here we want to do that on a larger scale with PLATO to get the mass radius, but also in particular the age of the system from the star. So now to wrap up this introduction, so with the PLATO mission, PLATO will combine the detection of the planet via photometric transits to determine the radius of the planet with astroseismology to get in particular the age of the system, and then follow by radial velocity observations from the ground to get the planetary masses. And with these parameters, we have the mean densities and we have the age, and we can put the planets detected by PLATO into, and this is just for illustration here, but to put into the context of planet evolution, terrestrial planet evolution. That's the big picture. So how does the PLATO satellite look like? Here is, you see it in the movie. This is how it is. And for a telescope, it is a very unusual design because it's not one single dish, but has 26 small cameras. And with this system, we get a very high, photometric range of magnitudes. We can go from very bright, relatively bright stars to relatively faint stars with the same camera. Why? Because we have to combine at the same time the requirement for transit detection, and that is observe many stars to detect with characterization, and that means we have to go for bright stars. Okay, so this is how it looks like. So we have 26 cameras which are mounted on an optical bench. You see this with this staircase-like appearance, and this optical bench with the cameras then is mounted on a satellite platform with a shield protecting it against the sun. So the sun is always in the back of the satellite, and here we have the panels for the whole thing. Size, I should say, with these 8 meters, yeah, and then the satellite itself about 3 by 4 meters. So the payload, as I said, the payload consists of cameras with 6 lenses. And so the photons come in through this telescope, what we call this the telescope part, onto a CCD detector with 4 CCDs in each focal plane, converted into electrons and then analog digital units by the front-end electronics. From there, these CCD images go into the main electronic unit and finally to the central data processing unit on the satellite. And this here imagettes, that means little, in Kepler they call it postage stamps, so little cutouts of the big image are selected or light curves computed on board of the satellite will then go to the central board computer. Why are we not transferring the whole images to the ground? Well, it's simply because with 26 cameras and 4 big CCDs in each focal plane, we are producing so much data we cannot transfer all the full frames to ground. So we have to select beforehand which stars we want to observe and then transfer to the ground only the data for these stars. And this is happening here in the central computing system. But then these data are sent to the spacecraft, and the spacecraft sends it down to the ground stations of ESA. The instrument, I said already, 26 cameras. So let's have a look. Here's a movie that shows one of these cameras. The buffer, it has a 12 centimeter aperture, so relatively small, because we want to observe also bright stars. The buffer here is for radiation and protection against stray light. You see here the tube, and then on the bottom the focal plane. Inside the tube, you see here these lenses, as the camera now script. So these cameras are grouped into 4 groups with 6 cameras each. That makes 24. We call them normal cameras. And in addition, 2 cameras on the top here, which we call fast cameras. Fast because they have a very fast readout. Every 2.5 seconds, we get an image from the fast cameras. Why? Because they are connected to the AOCS, so to the pointing system of the satellite. We have to keep the satellite very, very stable in the sky. We really must keep the stars on the same pixel all the time. And all the time means for years. Or together, or at least every 3 months, because we have to rotate every 3 months to keep the sun in the back. So this is done via the fast cameras together with the satellite system. And the normal cameras are read out every 25 seconds. They operate in white light, so we get white light. And so these 4 groups are also mounted, the cameras are mounted fixed on the optical bench. You can't move them. And the 4 groups are spread a little bit apart to open the field of view. Here we have a field of view of PLATO. So one size, it's about 50 by 50 degrees. And in the center, we have all 24 cameras looking at the sky. And in the corners, it's 6 cameras. Sorry. I should say that with these cameras and CCDs on the focal plane, PLATO will be the largest digital camera ever flown to space. So it has a larger light-sensitive area, larger than the Gaia satellite, for example. So it will be a really big camera. And finally, to show you a little bit how this looks like in practice, because now we are in the phase of developing and building this instrument. The launch is foreseen, as I said, at the end of 2026. That means the flight models of the cameras have to be ready 24, 2 years typically before launch, 24, 25. And now we are in the phase C of such a project development. That means it's a phase where engineering models are built, testing is done, and the first flight model production starts. And in this image, in this slide, you can see several things. So to the left, we see here a mass and thermal dummy. That means you see the optical bench here, and you have people standing here, so you can get a better feeling for the size of the satellite. So this is just the optical bench. And on the optical bench, you see cameras. They are not real cameras. There's nothing inside. There are no lenses or anything inside. They are mass and thermal dummies. That means they have the same mass and the same thermal behavior as the real cameras. And they are used to test how the cameras would behave when they get into space and whether they would get too hot, for example, or disturb themselves. So we see this here at ESA. It was integrated in Munich and delivered from all parties to Munich, to Aerospace. Then from there, the optical bench came to ESA. And ESA has put this optical bench into a big vacuum tank. It's a bit difficult to see. You see here, you have to imagine a big hole in the ground. Yeah. Here's the hole where the optical bench entered the tank. You see it here again. If you look very hard, there's a person standing here next to it. So you get a feeling for the size again. And then this is closed. It's evacuated. And here we see an infrared image of the optical bench again. And the good message from this infrared image was that everything is fine, no problems, all the temperatures and the temperature distribution was as it should be. So this test was ticked off as successful. So very nice. On the instrument side, many things are happening, and I've just taken 3 examples here. In the upper picture here, we see the focal plane manufactured in Spain. with 4 placed CCDs inside, an engineering model. In the, let me jump to the bottom. In the bottom, we see a full data processing chain engineering model of a fast camera. And you see this doesn't look like a camera at all. So what do you see? So these are, the big rack here in the middle is a simulator specially built to simulate the behavior of the spacecraft. And the box from the left is the readout electronics of the fast camera, the power supply, and then the different elements of the onboard computers. Until, again, the data that would go through here come back into a simulator for the spacecraft again. So you see how what the engineers are doing. They are building all these engineering elements. Cameras are also built together. Here you see a real camera ready to go into this tank this is in the Netherlands. This tank is there to test the cameras and calibrate the cameras. And you can guess already, maybe from what I said, that the building of such a mission is a big endeavor, and in Europe it has many, many contributors. So here it's about the camera, so the payload contribution only. I'm not talking about the satellite platform and the optical bench. This is an industry consortium that is also well distributed, but just for this 26 cameras and the corresponding power supplies, computers, and so on. You see, it's a big consortium, about 800, almost 800 people are now in the consortium, about 100, 150 people working on the payload, I would guess, altogether. And you see the different elements come from all over Europe. For example, the CCDs are built under the contract of ESA, are built in the UK. Okay, there's front-end electronics, same as Germany. The focal plane from Spain, with the optics from and onboard computer from Italy. Testing to calibrate the cameras is such a big job that it's done in 3 places in parallel in Europe. And finally, we have Brazil here, who contributes to, and collaborates closely, in particular with our institute here, on the processing and the data chains of the fast cameras, which are very, very important because they guarantee the point. So I'm very happy to see this. It's a lot of fun to work together, and it's nice to have this collaboration with Brazil and also the continuation in the field from Corona to PLATO. So finally, when this is built, what will happen? PLATO will launch N26, beginning 27 will start operating. The nominal mission duration time that we have been given by ESA is 4 years, and the baseline plan now is to observe 2 years on the southern hemisphere, 2 years on the northern hemisphere, where the order of where to start is not decided yet. We have to fix the final observing program 2 years before launch. That's still 2 years ahead, but not so much ahead. And preliminary positions on the sky where PLATO could be pointing are defined simply by the fact that we always have to have the sun in our back and not stray light, not too much stray light. So we will have roughly these regions, but the exact position of the field is not defined yet, where exactly in these regions. And the blue pattern here is the PLATO field of view, and this pink pattern, this is the Kepler mission field of view. So you get a comparison of the sizes of the 2 missions of the field of view. Of course, we can think about other alternatives, how to use the 4 years. And most important, the design of the satellite and the testing is such that we can have full performance until 6.5 years after launch. And the satellite will have consumables for 8 years mission duration. So in principle, the satellite can be operated 8 years. And of course, we all hope and we will go for mission extensions, because the longer your light curve baseline is, the higher is your chance to detect an Earth around the sun. Remember, with an Earth around the sun, we only have 1 transit per year. And that is not much in 4 years, or 2 years observation duration. And PLATO will observe 15,000 stars in its prime sample. And for this, we will get the very high precision. And in addition, we have a set of more than 200,000 stars with less precision. in radius and no astroseismology, but for statistics, so to follow up and what Kepler started on the general statistics of planet populations. And in addition, we have some index. So for you who want to know more about the input catalog, I've just added here these two things. I think I'll skip this now. This is just showing our computations, what we expect. Do we really reach the radius precision we have promised? And yes, indeed, we will reach it. Our computations show that we will indeed reach the 5% radius precision for an Earth around the Sun. And this slide is mainly to remind me to tell you an Earth around the Sun is our reference case, but at the same time, it's the most difficult case. So for larger planets, we will get even higher precision. Yeah. And for planets that are closer to the star, so we can add more transits, get better signal to Earth, we will get higher precision. So this will really be at the limit of what can be done. We will have a great ground-based program. That is, the ground-based follow-up teams are now organizing themselves to have the required resources to get the masses for the planets, in particular the small planets. This is really time-consuming. Yeah, and this is I'm coming now to an end to say, indeed, PLATO is here, and I don't go into this. You can look at this slide later on. It's in the middle, and there are many more missions to come. There's Ariel to come to look at atmospheres. There are many ideas around to look at habitable planets and biosignatures. And finally, I think I would like it to leave it with this here. Are there planets out there? I think this is what how the whole field started. And this we can answer. We can say yes. Every star has a planet. But with PLATO, we want to be able to tell you how many of these are planets that could be Earth-like. So with this, I stop. Thank you very much for your attention.
Okay, thank you very much, Heike. Very, very nice talk. Who wants to make questions? Please raise your hand. Marcelo, go ahead.
Hello, can you hear me?
Yes.
Yes.
Okay, thank you so much for this very, very nice talk. It was really good. So I have a curiosity. So compared to Kepler and TESS missions, what is exactly the advantage of the PLATO, especially related to the minimal flux variation detection, also the minimal planet size detection?
I don't have this slide here. I have a comparison. But in words is our effective aperture is a bit smaller than Kepler. It's about 60 centimeters square, and the Kepler was 90. Okay, and but due to the fact that we have these individual cameras, our main our magnitude range that we investigate is brighter. Most of the planets detected by Kepler were around stars about 15th magnitude. And this is too faint for follow-up for masses on a big scale. That's why you have relatively little. If you go back to the numbers now. Here. So that's why we have, although we have 5,000 planets known today, confirmed planets, we have relatively little, so only a fifth of them with known masses and radii. This is mainly because the Kepler planets targets were too faint. And so what PLATO will do is really, with the small apertures, we go for brighter stars. And this was also realized for TESS. Yeah, TESS has adopted this idea of PLATO. PLATO was proposed before TESS, so it was. So TESS does the same, but TESS focuses on the smaller, on planets with up to 30 days orbital period. So TESS explores this part of the diagram. That's why I'm also not emphasizing so much the Emdorf sample of PLATO, because it will be done, the habitable zone of Emdorf should be done by TESS, or is done by TESS. Plato will also have some M dwarfs in its sample, and we will then do the planets that are beyond the habitable zone. This is also interesting, obviously. But that's the main. So Plato's target range is really here. Is this answering your question? I'm not sure.
Yes. But I'm in doubt concerning one of your last slides when you said that Plato, you have 2 long pointings for 2 years. So this means that the same sky region will be observing during 2 years. Is that right?
Yeah. So what we've done is we have done, originally we wanted to have 6 years, but ESA only gave us 4 years because this is the standard operation duration time they use for these kind of missions. So we did calculations to see if we, with the signal to noise with Plato, we can get in 2 years, and also taking the Kepler example and inserting and seeing what Kepler could do, we can detect an Earth around the sun in 2 years. But of course, this is not, everything has to work fine. Yeah, and of course, you want to know more. I'm not, I'm not defending the 4 years. I've not asked for 3 years. We wanted more. Yeah. So with this, it's at the end now, it's a compromise between the number. So to detect the planets really that we want to detect, to observe 15 to 20,000 stars with high precision, we do need 2 fields. If we say we want to focus on an Earth around the sun and prefer to stay, for example, the 4 years on one field, of course, the absolute number of planets will go down. Yeah. And that is a trade-off. And this discussion about what to do, where to start the pointing, how to make a trade-off, it is starting now inside the team. And in some way, we'll also bring it to the community, or we listen to what the community says. But there's a trade-off to make. This is clear. And we all, let's be honest, even we want to go here. Yeah. This is, I think we all share this. Yeah.
Okay. Okay, thank you very much.
Okay, Simone, please.
Hi, so thank you for your talk. I have a question regarding the stellar ages. Since the stellar ages are important parameter for to constrain the stellar evolution models, and is it possible to constrain the stellar ages using the evolutionary stage of the disks or in planetary systems or protoplanetary systems in this phase, in the early phases of the stellar evolution?
I'm not sure I fully understood your question. It is about constraining the stellar or the planetary parameters in the early stages of planet evolution.
To constrain the stellar ages using the disk parameters, because since the formation of the planetary disk is related to the stellar age, but I think the different phases of the disk evolution depends on the stellar parameters, right?
Yeah, that's right. And what we want to do with Plato is to get, for solar-like stars, create kind of benchmark cases where we improve the stellar models. Now I should not say we, it's stellar colleagues in the team. I'm not a stellar scientist, but what they have done is indeed they formed working groups to study this and improve the stellar models with the help of these seismic data from Plato. We will not have astroseismic data for every whole star or for all 200,000 stars that Plato will observe. Yeah, but the idea is to use to get benchmark cases with improved stellar physics, also from red giant stars, from solar-like stars, and then with this calibrate the classical methods of age determination. And so we can apply an improved age determination from the Plato data to all stars. of course, for the very early stars, we will not, probably not get the 10% accuracy. And so the 10% age accuracy we say for solar-like stars.
And do you expect observational differences from planets in different evolutionary stages? For example, a planet that has just been formed or in an early stage of formation, like the Earth, when it was hot enough before this, what's the word? Before before cooling, you know, just after the formation. So is it possible to identify in which phase of the planet formation will be the planets according to the G-scan to?
Yeah. So let me go to the illustration maybe. So in this phase, so the idea is
Yes.
to get the age of the star is present. So
Mhm.
we know whether the star is just a few tens of millions years old. Since planet formation is so fast, we can take the age of the star equivalent to the age of the planet. Okay, and so we know we have a very young system. Then we would expect the planet to be in this stage. Yeah. At the end, the whole thing is always a comparison of what we think how planets evolve from what we know from the solar system, and then apply it to the other systems. And at the end, it's a combination of what we know from planet evolution in the solar system with the upcoming missions. Like if you see here, PLATO is addressing the population thing. We are not doing a deep investigation of one target. The Ariel mission will investigate mainly gas giant planets, atmospheres. Maybe some cases like planets around M dwarfs. James Webb is now up. James Webb can investigate planets around M dwarfs. And for example, such a planet that is now a hot terrestrial planet, so like Coro 7b, or a planet that is so close to the star that it has a molten surface, is like a planet, like a young Earth, but like a young Earth. You know? So we can learn how to get observables from the planets that we know today, although they are not Earth-like, but we can learn how to study hot planets, for example. But what we need at the end is another generation of telescopes to really investigate the details and the atmospheres and the details of these small planets. That is something for the 30s, 40s, and beyond, where we really have telescopes with really big dishes and spectroscopy. So, well, it's a puzzle, yeah. And PLATO is not solving the whole story, because terrestrial planet evolution is so complex, and we are still struggling in the solar system that we cannot imagine just radius, mass, density, and age solves everything. But it is an important piece in the puzzle. Together with James Webb, it will form a very powerful tool, Ariel for the gaseous, and then we have to encourage the next generation to build something bigger.
Great, thanks.
Yeah, sometimes I wish I would be a bit younger, so I thought, yeah, we could be here also. Okay, we can only go the step. It's like running. I don't know how to call this. You know, the runs where you have to give to the next. Yeah.
Okay, I have a question concerning, I think you mentioned that you will download only a portion of the data, the portion that interests to you, because I presume that, okay, the satellite will be pointing to some region of the sky to be defined, and you will measure the flux of anything in that field of view, anything, even asteroids and galaxies and everything.
No,
but you will take only those the flux of those objects that interest you. But what will happen with the rest of the information? It will be discarded. It will remain in the satellite. It is expected sometime in the future to recover that or not.
Yeah, very good point. So we have to give an input catalog, yeah, and there's work done and it's described here in these publications. And yeah, I think I forgot to say that. I think I forgot to say that, and I should say it now. Thanks for reminding. There is a guest observer program and a complementary science program for PLATO. So I have focused here on the exoplanet side of the story. Of course, there is more, and there's a lot of stellar science you can do. There's even science on solar system, whatever you can do, extragalactic. And so there is a complementary science program. 8% of the data rate of PLATO will go into this guest observer program, where everybody in the community can apply, can write a proposal. ESA will launch these calls. The first call will come half a year before launch, and then again when we move to a new field, and the whole community can hand in proposals. The proposals will be selected by the ESA science working team. And so we are looking forward to a really great complementary science guest observer program. And if you look at the experience from Kourou, but also Kepler and even Cheops, this program produces an enormous amount of results and publications, and sometimes outnumbers the exoplanet publications, because the application of these data is so broad. So that is we don't talk about it now here so much, because it's not the driver or the origin to build the mission. But if you think about legacy, there is a huge legacy in this guest observer program, and I can only encourage you, look at it when the call comes, and please hand in many proposals.
Okay, thank you. Do we have more questions?
Fernando,
Yes.
I sent you a message with a question from the YouTube.
Ah, okay.
It's in the chat.
Ah, it's in the chat. Okay. What is the question? Okay. Can you talk a little bit more about ground telescope follow-ups, radial velocity, Rossiter-McLaughlin effect for mass determination?
Yes.
It's a question for Marco Antonio Petersen.
Okay. As you see here, the ground-based part is an integral part of the mission, because when we talk about characterization, it really means mean density, and that means we need the mass. And the PLATO consortium is now organizing this ground-based observation program. Organizing means we are managing it. We will offer the facilities to make available the detected transit candidates. And we want to have a coordinated approach, not to waste too much telescope time. And when we come to the very small targets on long orbital periods, it will need a lot of telescope time from big telescopes, and it would be a real shame if, for example, a team observes one target and another team knows already it's not a planet. Yeah. So we need some coordination. We are setting it up. To become part of the ground-based program, with own facilities or with manpower, is very welcome, and that needs an email either to me or to Stefan Audry in Geneva, who is coordinating it, but I would forward this email to him. So if people want to take part of this, don't hesitate, it's very welcome. This applies also to other parts of the PLATO mission. The PLATO consortium is very open for people to want to contribute.
Okay, thank you. Well,
Fernando,
see?
may I ask another question?
Yes, of course.
Yeah, because I'm looking this slide and came to my mind. Is it possible to have some kind of confusion between some long period pulsations and also a transit? Or is it easy to separate all of them?
No, it's true. And that's why you need radio velocity follow-up. That then will give you the decision. So that's why at the end you need radius and masses. And at that point you can tell it has been stellar or as a planet.
Okay, thank you. Thank you.
Okay, well, we thank again Dr. Heike Rauer for this wonderful talk and for accepting the invitation to take these few minutes to give us some information about this wonderful mission.
It was a pleasure.
Thank you to all. And I think that with this, we close this edition of the special courses of this year. So let's hope we meet again next year in another edition. Thank you very much to all.
Thank you all.
I don't know,
Thank you, Dr.
I don't know if
Heike.
Simone or Renato want to say something.
No, I just want to say thank you, everybody.
Same here.
We hope next year will be in person meeting, in person school. We hope so.
Yes. Thanks, everybody.
Okay,
Okay,
bye-bye.
thank you.
Thank
Ciao,
you.
ciao, bye-bye. Thank you very much.
Thank you very much.
Bye.
Simone, você tem que desligar o streaming, ou não?
Ah,